In this video, I'm going to show you guys how to solve for a system. It's called a compound system, in this case an ideal pulley with no friction. And you can see I've got a 5 kilogram object hanging from a string that's attached around a pulley to a 3 kilogram object. In order to solve this problem, the first thing I've got to do is establish a reference frame. Now in pulley systems, it's not like a simple system where to the right is positive and to the left is positive. In this case, because the objects are attached, while the 3 kilogram object is moving up, the 5 kilogram object is moving down. And so you can't say that the motion of the system is up and down at the same time. It just doesn't work very well. And so typically what we do is we just decide which way the pulley's rotation is going to be positive. And it doesn't matter which way you choose. I personally like to guess which side is going to win, meaning which side is going to drive the system. And in this case, I'm anticipating the 5 kilogram object to yank the string downward from its perspective. And so I've just chosen positive to be counterclockwise motion around the pulley. Which means that up for the 3 kilogram object is positive, down on the 5 kilogram object is positive. This is very important to do because most of the mistakes that are made on problems like this and more complicated ones are just forgetting which direction is positive and negative. And that's an avoidable mistake. There's really no excuse for that, to be honest. So I've got two objects in my system. We're assuming the rope is massless. I'm going to color code the forces, but before I'm going to do that, I'm going to draw a bubble diagram. Identifying my system is really useful because I'm going to redefine the system halfway through the problem. So I've got the 5 kilogram mass, I've got the 3 kilogram mass, and I've got the rope that looks like this. I'm intentionally leaving the pulley out of the system, but you can include it if you want, just because it is not really interacting with anything if it's an ideal pulley, which means it doesn't have mass or dimension or really anything that makes it interesting. It's really just there to change the direction. The 5 kilogram object interacts with the rope in that way, and the 3 kilogram mass through tension. All of these objects are interacting with the Earth's gravitational field, so there will be gravitational force, but we're going to assume that the rope is massless, and if the rope is massless, then there's no gravitational force on the rope. Alright, so I'm going to draw a force diagram for each of these objects. So there's that, and there's that. Actually, I said I was going to color code it, so I'm going to change the color of this interaction to be red. Okay, for the 3 kilogram object, the gravitational force is going to pull it straight down, and that'll be with 30 newtons. That's in the negative direction. And for the 5 kilogram object, I've got 50 newtons from the gravitational force. And the rope is going to be pulling this object up, and the rope is going to be pulling this object up. Alright, so I've got one system with two objects and a rope. The whole idea here is that the whole system accelerates together, and so it would be wise to analyze this entire problem as if those two objects were really just one big object. So what I'm going to do is I'm going to redefine my system to include all of those objects. And interacting with that system is just the gravitational force of the Earth. In essence, what I've done is I've just basically turned the tension force from the rope into an internal force. Now, what does that mean? It means that my new system is equal to the mass of all of the objects inside of it, 8 kilograms. Now, what do I do to solve for the unbalanced force? Here's the technique. What you're going to do is you're going to rotate one of the force diagrams in such a way to where you can smush that tension force of the rope. And so what I mean by that is the second diagram with the 3 kilogram object. If I've got 30 pointing down this way, and I've got the tension pointing upward like so, if I were to rotate this diagram 100 degrees, now I've got the force diagram such that the tension force is pointing down and the gravitational force is pointing in the opposite direction. It's as if I've kind of slid the object around the pulley. Now if I slide this force over and smush it right on top, it effectively cancels out that tension force. And so on my force diagram, and this is the technique that it's kind of tricky to understand, I guess. When I redraw the system's force diagram, the tension force has canceled out because that force is now within the system. If you wanted to include that one, you might as well include all of the intermolecular forces that are mucking things up too. Well, anyways, if you cancel out the blue tension forces, this is what the system's force diagram would look like. The system's mass is 8 kilograms because that's what sits inside the big purple dotted line. And pulling down on the system is 50 newtons from the Earth, and holding the system up is the 30 newtons from the mass on the opposite side. To determine the acceleration of the object, I'm going to use Newton's second law, which states that the sum of the forces is equal to the system's mass times its acceleration. And if you recall, we determined that on this side, any motion's positive, that side's negative. So 50 newtons plus a negative 30 newtons. Remember, to sum is to add, and so you can add negative numbers. Don't double subtract, please. The unbalanced force is equal to 20 newtons. The acceleration is going to equal 20 newtons divided by 8 kilograms, which is going to equal 2.5 newtons per kilogram. And this is the acceleration of all of the objects, the 5 kilogram mass, the rope, and the 3 kilogram object in that system. Remember, the trick is to rotate and smush to turn the force of the rope into an internal force. Thank you guys very much.